Okay, so let's start the class. Welcome back. Today we are going to continue our discussion on the turbojet engines. Hopefully we will finish our the analysis of a full turbojet engine. So meaning that we will cover the nozzle analysis and we will cover we will talk about an overall engine analysis. Okay, I think we stopped here. Solving an example for turbine. So this is an example that's actually that can be a good refreshment for you guys as well. So it refreshes your memory on the equations and everything. So let's solve this together. And the example is telling us consider an uncooled gas turbine with its inlet condition the same as the exit condition of the combustor described in the previous example, which if you recall from the previous example, the temperature was 1390 Kelvin, right? If you go back to the example we solved, this is the temperature you should have. The turbine adiabatic efficiency is 88%. Turbine produces a shaft power to drive the compressor and other accessories at 45 megawatts. Assuming the gas properties in the turbine are the same as the burner exit in the previous example, which means that gamma is 1.3 and CP is I don't remember what CP was. It should be 1.156 kilojoules per kilogram Kelvin. We want to find the turbine exit total temperature, which is TT5 in Kelvin. Okay. So, what do you think we should do? We have the shaft power, we have the turbine power, we have the inlet properties, inlet temperature, and we also have the mass flow rate, right? From the previous example. What was the mass flow rate in the previous example? 50. That's after the combustor. 50.02 was the ratio though, right? Okay. Let's go with 50 because, pardon me? Okay, 51. Yeah, 51. As the fuel to air ratio is 2%, right? So 51. Okay. So we have m dot, we have the inlet properties, and we have the shaft power, turbine power. How can we calculate the turbine total exit temperature? What was the equation we had for the shaft power? Anyone? Exactly. So m dot t ht4 minus ht5, right? Can we replace these enthalpies with anything? Cp tt4 minus tt5 in parentheses, right? So we have m dot Cp tt4 minus tt5, right? What happened? So you just plug in the values. What do we have for P of T? 45 megawatts. What do we have for m dot? We have 51, right? What do we have for Cp? We have, what was the value of Cp? Can you go back and check? 1156. Yeah, 1156, yeah. No, tau of C. Temperature ratio of combustor, of a compressor, sorry, right? So the adiabatic efficiency is always the symbol we use for adiabatic efficiency is this, eta. Okay, eta for adiabatic efficiency, tau for temperature ratio, and pi for pressure ratio, right? Make sure you don't confuse them. Okay. 626.7, exactly. So the TT5 is going to be 626.7 Kelvin, as Ryan mentioned. So part B is asking us to find the polytropic efficiency, E of T. How can we find the polytropic efficiency? What do we have? The first thing you need to look at is you have to look at what we have here. We have the temperatures, which means that we will have the temperature ratio, right? Tau of T, right? What else do we have? We have the adiabatic efficiency. Do we have any equation that relates the polytropic efficiency to the adiabatic efficiency and the temperature ratio? We don't have the pressure ratio. Exactly. So this is the equation we are looking for. Eta of T is equals to 1 minus tau of T over 1 minus tau of T to the power 1 over E of T, right? We have eta of T, we have tau of T. We want to calculate E of T. What you want to do is to get an equation that calculates E of T for you, right? The polytropic efficiency. So you can have 1 minus tau of T to the power 1 E of T equal to 1 minus tau of T over eta of T, right? You can take the 1 to the other side and also the negative sign. So tau of T to the power E of T is going to be equal to 1 minus tau of T over eta of T. Okay, what will happen if we take the natural log from the both sides? I'm going to write up here. You will have 1 over E of T natural log of tau of T, right, equal to natural log of 1 minus tau of T over eta of T, right? Is this correct? Then we can take this natural log to the other side, right? And then take the inverse of the whole equation. You're going to get E of T natural log of tau of T over natural log of 1 minus tau of T over eta of T. Does this make sense? Okay. Yeah, of course, you can simplify it a little further. This is the ratio of 2 natural logs. So what does it mean? I mean, how can we simplify this further? Let me ask you that question. No, I gave you the wrong clue. Don't forget about the clue I gave you. How can we simplify this a little further? We don't need to simplify it. Let's just plug in the numbers and find it. Yeah. Yeah, forget about it. It's gonna be another mess. But if you were interested in simplifying further, you can actually make this phrase here, make it a ratio. And what would happen if you do it a ratio? If you make it a ratio, you can divide it to a subtraction natural log, right? And then you'll see where it goes from there. I won't call it a simplification that much, it's just a different approach. So plug in the values in this equation. And tell me what kind of E of t you will get. TT4 was 1390. .814. That's it. Yeah. So let me write the equation again. E of t is equals to natural log of tau of t over natural log of 1 minus 1. I forgot the equation. 1 minus tau of t over. That was it, right? Yep. Okay. So this was the equation. You plug in the values, and you get E of t to be 0.814. Okay. Let's take a look at part C. Part C is asking us to find the turbine exit total pressure. Okay. From the previous example, we saw that PT4 was actually 1.92 megapascals, if you recall. So what should we do? How can we find the exit pressure? Pi t equals to tau of t to the power gamma over E of t, right? That's it, right? And this is a power. Let me rewrite this. So we have the tau of t. You have the tau of t, you have the gamma, which is 1.3. You have the E of t, just plug in the values, you get the pressure ratio. And this pressure ratio is, what do you think? No, you have to elaborate on your guess. It cannot be just a guess. So gamma of air, we usually assume gamma of air is 1.4, right? But is the whatever that is going into the turbine, is it air? It's air plus fuel, right? So your gamma, it should be the one that is not 1.4, right? 1.3. Okay. What did we get? What did you get for the pressure ratio? Are you expecting to see a pressure ratio higher than 1 or lower than 1? So my question is this a compression process or an expansion process? Expansion. So you expect to see a pressure ratio lower or higher than 1? Lower, yeah. Do we have a solution? $37. So for pi of t, I assume you got 0.019, right? And PT5 using that should be 37.26 kilopascals. So you see the temperature has dropped significantly, right? And the part D is asking us to find the turbine shaft power, which this part of the question is very pointless to me because we were already given the shaft power and it's the thing we used to do a lot of calculations, right? We don't need to go back and calculate it again. Okay, is there any questions here? Okay, so let's move on to nozzles. Here you will see a schematic of a nozzle and the pressure distribution of a nozzle. But the question I have for you, and you always have to keep in mind that this layer, the later part of the nozzle is called the boat tail of the nozzle. That's the throat area, the exhaust area of the nozzle. And the nozzle is essentially the exhaust system of the turbojet. But then the question is, what is the primary function of this exhaust system? What do you guys think? What does it do to the waste? Mixed out? But you don't need to have an exhaust system. You can just like use the exit of the turbine or the whatever you have afterburn as the exhaust, right? You can do the same thing for a car as well. You can just use the engine exhaust as the exhaust. You don't need to have a system, right? But the car is a different mechanism. We have the exhaust system in a car for a different reason. But why do we have? My question is about the engines, turbojet engines, right? What? Exactly. We want to speed up the flow at the exit, right? So what was the job of a diffuser? We wanted to decelerate the flow. What is the job of an exhaust? We want to accelerate the flow. And why do we want to do that? Why do we want to accelerate the flow? Exactly. So the exit velocity is the main thing that is responsible for your thrust, right? So if you can increase your exhaust velocity, which is V9, this Fg was the gross thrust, if you recall, right? If you increase your V9, you are going to get a highest thrust value. Okay? And if you recall from our previous discussion, m dot V9 is called the momentum thrust, and the delta P multiplied by the exit velocity is called the pressure thrust. You always have to keep in mind that the nozzles usually produce a signature, right? Some sort of infrared radiation, a thermal plume, smoke, or some sort of acoustic signature. And these signatures are different from nozzles, so you can actually characterize nozzles based on the signature they provide at the exit. But we're not going to go over the signatures and their importance. That's out of the scope of this course. But so we talked about one of the differences between the nozzle and a diffuser, the flow distillation versus the flow acceleration. What is the other difference between the diffuser and nozzle, right? What do you think? What do you think the other difference is? So we talked about the velocity part, right? What is the effect of a diffuser on the pressure this time? Let's talk about pressure. We talked about velocity. A nozzle accelerates the flow, so higher velocity, right? A diffuser decelerates the flow. What will happen to pressure in a diffuser and in a nozzle? Or what kind of a pressure gradients you will get in a diffuser? Okay, so essentially because of that adverse pressure gradients, we have to be mindful of the viscous losses, right? What can you say about the nozzle? Barrel separation is not as important because it is very unlikely for it to happen, right? And if it happens, it's not going to have that because of effect, right? For whatever reason. So in nozzles, we have favorable pressure gradients. Compared to the adverse pressure gradients we have in a diffuser. Okay. So let's talk about the some rules that we have in a nozzle. These are essentially some natural rules that will definitely happen, that should happen, and your design should always be mindful of this, right? The first rule is that if your jet Mach number, which is the exhaust Mach number, is smaller than 1, meaning that you are in the subsonic region, your jet pressure, your jet static pressure, must be equal to the ambient pressure. So this is M of jet is actually M9, and P of jet is P9. Ambient pressure is P0, right? P0. But what was this condition? What did we call this specific situation when your P jet is equals to the ambient pressure? A perfectly expanded nozzle, exactly. So that's your rule number 2. If your P jet is equals to the ambient pressure, then you have a perfectly expanded nozzle, which will result in the maximum gross thrust. So based on these 2 rules, what can you conclude for the thrust of a subsonic jet? We know that a perfectly expanded nozzle will result in the maximum gross thrust, right? That's rule 2, rule number 2. But rule number 1 is telling us that in a subsonic region, in a subsonic regime, your static pressure is going to be equal, at the exit is going to be equal to the ambient pressure, ambient static pressure. Okay, so exactly, unless you are told otherwise, right? So you can always, in a subsonic jet flow, you can always assume that you are dealing with a perfectly expanded nozzle, which will result in a maximum gross thrust. Okay, rule number 3 talks about the NPR, which stands for nozzle pressure ratio. Right? We define NPR, and this is so these two rules apply to any type of nozzle, right? But mostly a convergent nozzle. But rule number 3 is specifically including a convergent divergent nozzle as well. Convergent, let me actually, I think I have it here. Yeah, this type of nozzle. But we need to talk about the definition of NPR. Have we talked about this before?
I have a question about the maximum growth rate. So if you go back to the equation and say that the nozzle was overexpanded, then wouldn't P9 greater than P0 equal positive pressure growth?
Okay. But what will be the effect on the? We talked about this, if you recall. What will be the effect of it on the velocity, though? So will you get the same velocity for a perfectly expanded nozzle at the same situation? The only difference being the nozzle expansion, perfectly expanded over expansion or under expansion. Yeah. So that's actually that. So the comparison is not. My point is the comparison is not that simple, right? That's it. Okay. So let's talk about this definition of nozzle pressure ratio. The nozzle pressure ratio is actually defined as, that's something that we need to make sure that we are clear, because it is not mentioned in the book, and they just assume you already know this. Nozzle pressure ratio is defined as your inlet pressure here, PT7, for example, the total inlet pressure, divided by the ambient pressure. So that's your nozzle pressure ratio. But we also have something called the area ratio, nozzle area ratio. But the nozzle area ratio is your exit ratio. Where do we have the area ratio? Exit, we don't have. Is defined as the exit ratio, which in this case for a convergent divergent nozzle is 9 by the throat ratio, okay, which is 8 here. Okay, so the area ratio in the nozzle is throat area, the exit area, exhaust area divided by the throat area. The pressure ratio is defined as the inlet pressure divided by the ambient pressure. Okay, so rule number 3 is telling us that we have a critical value of pressure ratio, the nozzle pressure ratio, at which the flow will be choked at the throat of the nozzle, right? So for any pressure ratio higher than this critical value, the nozzle throat velocity is going to be sonic. We will have the sonic condition, or the throat will be choked, as we have seen before. Rule number 4 is more of an approximation than a rule. So this choking condition is telling us that this choking condition, or your critical value, NPR, is actually very close to 2, which means that it happens when your total pressure at the inlet of the nozzle is twice the ambient pressure. Okay? Does that make sense? We don't need to go through the proof of this, and your book hasn't done the proof, but this is an approximation essentially. It's a pretty close approximation. Okay, so what we want to discuss after is what's going to happen to a convergent divergent nozzle if your NPR is higher than 2, right? If the pressure ratio is higher than 2. what will happen? Okay. You will have so you will always have a shock. Is that what's going to happen? So let me rephrase the question. The question that one of the rules told us that if your pressure ratio is larger than 2, then we will have choking. And I'm telling you that let's say your pressure ratio is larger than 2. So I'm actually telling you is that I'm telling you that we will have choking at station 8, right, which is your throat. So what will happen in a jet when you have choking? And this is a continuation, an expansion of what we have discussed before, right? We're not going to do any like mathematical analysis on this. It's just a discussion, right? But it's going to be a little harder than what we have seen before analytically. What do you think, guys? Chime in. Exactly. What's going to happen to pressure? The pressure ratio, so the pressure at the exit is going to be smaller than the, is that what you're saying? Yeah, but the rule 1 told us your ambient pressure must be equal to the exhaust pressure, right? But the thing is, you will have the perfectly expanded nozzle. So that's the rule. That's gonna. That's the question you want to answer. It is a convergent divergent nozzle. So the choking happens at the throat, right? That's the idea. Wouldn't the velocity decrease? Is that what you're, the velocity decrease? So let's say in your condition, we are not talking about, okay. Is that going to always happen? Look at this plot. Look at this figure here. I'm talking about this figure. What do you understand from this? Let's actually go from here. What do you understand from this figure? This is your pressure divided by the inlet pressure, right? Of course, at the inlet it is 1. It becomes smaller, smaller, smaller. And then it divides to 2, which is telling us that we may have 2 different solutions, right? So we may have a subsonic solution and a supersonic. Go ahead. Okay, that we are getting somewhere there. Okay, so not based on the ambient pressure, based on the back pressure here, which is of course a function of the ambient pressure, right? But so if you have a very high back pressure, what's going to happen is that you're going to get this after the throat area, after the choking. What's going to happen is that your divergent part of the nozzle will act as a diffuser, right? So you're going to get some expansion, and then you will have a subsonic solution. So the flow adjustment will be in a way that you will get a subsonic solution after the throat, actually. And then your goal is, your pressure is going to increase compared to the inlet pressure. Make sense? But if you have a very low back pressure, your convergent divergent nozzle will continue acting as a nozzle, right? Which means that you will have the what are we gonna have if this acts as a nozzle? Okay, yeah, exactly. So it's gonna increase in speed, but it is not a sustainable solution as we have already seen, right? Right? We have already seen this. So what's gonna happen inside is that based on that back pressure, again, you will get different solutions. You either will get a normal shock to bring the pressure up, or you will, based on the back pressure, based on your back pressure, you will get an oblique shock, which will bring your pressure up again. And if your ambient pressure is actually very low, very, very low, if your back pressure is very low, which talks about the very low ambient pressure, you will actually get an expansion wave at the end of the nozzle to reduce the pressure a little, even a little further. So let's just start from Joshua this time. I just want to make sure that we are all clear on what is happening here. Yeah, what you understood from what I explained. No. Where is 0.5? That's actually that's one of the confusions I didn't want to. That's pressure inside the nozzle, right? Pressure as a function of x. So the nozzle pressure ratio is PT7 compared to the ambient pressure, right? They get to have the same solution for the choking condition at the throat, but this 0.5 doesn't refer to NPR, right? Okay, yeah, continue. Because of instability of that condition, right? We have already seen that. Okay, so let's go to near left this time.
It's a little bit of everything. You want one direction, it's low pressure, you want the other high pressure. Supersonic at top, subsonic at the bottom.
Okay, so I just want to make sure that you are clear. Are you all? Yes. No. Look at this figure, right? This figure goes from 0. That's a different too. That's a different. They give you the same value when you have the choking, right? But this pressure here is the pressure at the throat, right? NPR is the comparison between the inlet pressure and the ambient pressure. Okay. Let's go back. I actually have it here. So this is P naught, right? But this pressure here is a P of X. That's why you see it's changing. The ambient pressure shouldn't change with X inside the nozzle, right? Does it make sense? So essentially, if you have a very high P naught, which means that you have a very high back pressure here, this is going to be your, actually, if you have a very high back pressure and high ambient pressure, which means that you will have a high back pressure, this is going to be your pressure distribution inside the convergent divergent nozzle, right? If you have a very low ambient pressure, let's say you will get a normal shock, not a very low, but a low ambient pressure, this is going to be what you're getting. So you're going to get this part, then the supersonic solution, then normal shock wave. Does it make sense?
Why is it dependent on like T naught, like right after T naught? Why is it dependent on back pressure? Because after it becomes like sonic, it can no longer like see the upstream pressure, so it's all dependent on. It should be dependent on the pressure of the exit to meet those conditions, rather than because there's the pressure at.
That's correct, but both of those pressures are actually essentially not very close to each other, but are related to each other. When you have a high back pressure, it means that you have a high ambient pressure, right? And here at the exit, you have the ambient pressure. Does it make sense? Which part of it doesn't make sense?
I just don't like when you say like it depends on backflow, but I like to think that it depends on like, the exit condition at the mouth.
Not backflow, back pressure, right? You know, but back pressure is essentially means that the pressure before this station, right? If you have a high back pressure, you have a high ambient pressure as well, which is your exhaust pressure. Does it make sense? Huh? Hopefully. Okay, rule 5. So all of this discussion will lead to this conclusion eventually, that all of these complex phenomena happens because the static pressure must be continuous across the slipstream of a jet exhaust plume. Yeah. And keep in mind that we are talking about the subsonic turbojet engine. We are not talking about supersonic condition. Okay. So moving on to the analysis of the efficiency of the nozzle. Let's have the HS diagram. The HS diagram, we are going from station 7 to station 9. You have a question? So we are going from station 7 to station 9. What are the characteristics of this process, right? Is this an adiabatic process in a nozzle? Is this an adiabatic process? Yes, it is, right? Is this an isentropic process? No, of course. In reality, it is not an isentropic process because of all the losses, right? So the ideal condition or the efficiency is going to be we can calculate the efficiency by comparing the actual process that is happening here, right, with the isentropic process. Okay. Then the other question I have for you guys is that it's an adiabatic process. It is written there. So HT7, the total enthalpy at the station 7 doesn't really change, right? At the exhaust, it's going to be equal to the exhaust and total enthalpy, right? But we will see a huge pressure drop, the total pressure drop in the nozzle. And we define the pressure ratio of a nozzle as PT9 over PT7. Okay. So how can we define the efficiency based on this information here? How do we define the efficiency? The actual process over the isentropic process, right? Just find that ratio and you will be able to find the efficiency. So HT7 minus H9 divided by HT7 minus H9S. Of course, if you were to find the isentropic velocities, which we don't use that much really, you can use the velocities to exhaust velocity and the isentropic exhaust velocity to calculate that efficiency. Okay. So let's divide the efficiency equation by HT7, right? We can have 1 minus HT9 if you divide it by HT7. We can have 1 minus H9 divided by HT9 and 1 minus H9S divided by HT7. Okay. And we can use the isentropic relationships here at the denominator, right? That's pretty obvious, P9 over P7. But what can we do for the numerator, right? This is not an isentropic relationship, is it? No, this is not an isentropic process. But what we can say is that we can replace HT7 with HT9. So here it should be HT9. Because the idea was HT7 and HT9 are equal, right? That's the idea. And we always know that the going from a static to the total condition, we go through an isentropic process. That was the definition of a total condition, right? So we can use the isentropic relationships for the same station when we go from the static to the total, right? So we're going to replace the H9 over HT9 by P9 divided by PT9 to the power gamma minus 1 over gamma, that which is the isentropic relationship you have. Okay, so the next step is to multiply whatever we have by PT7 divided by P9 to the power gamma minus 1 divided by gamma. So what we're going to get, let me go back. So we want to multiply everything by PT7 divided by P9 to the power gamma minus 1 over gamma. Okay. So you're going to get PT7 over P9 here to the power gamma whatever. You're going to get 1 here. You're going to get PT7, PT9 to the power gamma minus 1 here, right? And what are we going to get here? We're going to get PT7 divided by PT9, right? Because the P9s will cancel out. Which is 1 over your pressure ratio, right? The nozzle pressure ratio. And we can play with that, have a negative power, and make it a pressure ratio to the power negative gamma minus 1 over gamma. And we can also play with the PT7 over PT9 a little bit. Multiply and divide it by a P0. And what we're going to get is going to be this, PT7 divided by P0 multiplied by P0 divided by P9. So PT7 by P0 was the definition of the nozzle pressure ratio. Keep in mind that there's a difference between NPR and pi of n. We call both of them nozzle pressure ratio, but P9 is PT9 divided by PT7. NPR is PT7 divided by P0, right? So both of them are design parameters of a nozzle and a turbojet. You have to be mindful of the difference. So multiply by P9 over P0 over P9. You can replace that in the efficiency equation. This is what you are going to get. But if we are in, what's going to happen to this equation in a subsonic turbojet? Exactly. So P0 and P9 are going to be equal because of the perfect expansion, right? So your equation is going to be like this. Eta of n is going to be equal to NPR to the power gamma minus 1 divided by gamma minus pi of n to the power minus gamma minus 1 for gamma, and so on and so forth. From the figure on the left, you can see that the nozzle total pressure ratio, pi of n, is of course related to, we have that from the equation as well, of course related to the nozzle efficiency. As you increase the total pressure ratio, your efficiency will decrease, right? The maximum efficiency you're going to get is going to be at the total pressure ratio of 1. Okay. Why do we get that maximum pressure ratio? Why do we get that maximum adiabatic efficiency at the pressure ratio of 1? Maximum gross thrust. What is the pressure thrust? What was it? But the pressure thrust is P9 minus P1, right? And pi n, to answer your earlier statement, not the second one. Right? P9 minus P naught multiplied by A. That was your pressure thrust, right? So the perfect expansion doesn't really relate to pi of n, which is PT9 minus, divided by PT7, right? So these two really don't talk to each other that much. But you said something else. What was your second statement? There won't be any pressure losses, right? Okay, so you're going to get the best adiabatic efficiency, which will never happen, right? And so and also for higher NPRs, for higher nozzle pressure ratio, that's the inlet ratio of the nozzle compared to the ambient pressure, you are going to get a higher efficiency, right, for the same pressure ratio. Does it make sense? Let's say pressure ratio of 0.8. For NPR of 2, you're going to get 70% efficiency, adiabatic efficiency. For NPR of 10, you're going to get 92% efficiency, right? So for higher NPR, you're going to get a higher efficiency for the same pressure ratio. Is there any questions so far? No? Okay, so that's the discussion we're going to have for the nozzles. Let's summarize whatever we discussed in the nozzle. The primary function of a nozzle is to accelerate the gas efficiently. The gross thrust parameter signifies the nozzle's contribution to the thrust production. The gross thrust reaches a maximum when the nozzle is perfectly expanded. Real nozzle flows may still be considered as adiabatic. A nozzle pressure ratio that causes a Mach 1 flow at the throat is called the critical nozzle pressure ratio, and as a rule of thumb, we may remember that the critical pressure ratio is very close to 2, is approximately 2. There are two efficiency parameters that quantify losses or degree of irreversibility in a nozzle, and they are related: pressure ratio and efficiency. The nozzle losses manifest themselves as the total pressure loss all subsonic exhaust streams have P jet equals to P ambient. A perfect nozzle expansion means that the exit are equal, exit and the ambient pressure are equal. And an imperfect nozzle expansion is caused by a mismatch between the nozzle area ratio and the altitude of operation. We have talked about the under expansion and over expansion. So let's solve this example before moving on. We are asked to consider a convergent divergent nozzle with a pressure ratio NPR of 10. The gas properties are gamma equals to 1.33 and CP is equals to 1156 joules per kilogram Kelvin, and they remain constant in the nozzle. The nozzle adiabatic efficiency is 0.94. We want to calculate the pressure ratio. So let's do it. Let's calculate the pressure ratio. We have the NPR. So which equation do we want to use? Last one. I guess that's a little complex calculation. So I'm just going to give you the final answer here. Your pressure ratio is going to be 0.8335. Then let's solve part 2 and part 3. Let's try to solve part 2 here. We want to find the nozzle area ratio, which is A9 divided by A8. The exhaust, the nozzle exit area divided by the throat area, right? For a perfectly expanded nozzle. How can we find that? Yep. Because we are dealing with a subsonic condition. This is essentially a continuation of previous examples. Pi of n, that's 0.8335. Let's solve part C first. Okay. Let's find the nozzle exit Mach number, M9. How can we find that parameter? Which one? This one? This one? Are you talking about this one? Okay, do you have the isentropic velocity though? How would you go about finding the isentropic velocity? So this part C is actually needs a little bit of creativity, right? Let's think about it. Do we have any relationship that relates the pressure ratio to Mach number? Did we have any relationship? That's okay. Which one? So let me ask you this: what is it? How can we convert the total pressure to the static pressure? Total pressure is equals to what? What is the definition? What is the equation? Yeah. Plus 1 plus V squared over 2, right? Right? What's that? What you were saying something. Okay, what is that equation? To what? To the power. That's it, right? Okay. So that's essentially, there should be a 2 in there as well. Yeah. Oh, I already have the 2. You already told me. Yeah, that's right. So this, actually, if you recall, maybe I should give you this in a quiz, because I thought we got here from this equation, right? So this is essentially using the definition. Okay, so we have this equation. I think I need to use that thing that relates the total condition to the static condition using the 1 plus gamma minus 1 m squared over 2 to gamma minus 1 over gamma, right? That's the equation, right? Gamma over gamma minus 1. That this is the equation, right? So we have an equation that relates the total condition to the static condition using the Mach number. Okay. Okay, what will happen to this equation if you apply the equation to station 9, your exit condition? What will happen to it? It will be PT9. It won't be 0. It will be PT9 divided by P9 equals to 1 plus gamma minus 1 M9 divided by 2 gamma over gamma minus 1, right? So if we had PT9 and P9, or if we had this ratio, we could easily find M9. Okay, but do we have this ratio? The NPR. So what is the definition of NPR? No, what? Which pressures? The ratio of which pressures? PT7 over P0, right? So no, we cannot use NPR. What did we just calculate? Which is 7, right? And are we assuming that it is a perfectly expanded nozzle? Yes, so P0 and P9 are the same. So essentially NPR can be PT7 divided by P9, right? Whereas P0 and P9 are the same. What will happen if we multiply these two? We are going to get PT7. If we do the multiplication, you're going to get PT9, divided by P9. So you're going to get the pressure ratio you need, right? Okay, so let's do that. And then find the Mach number. Yeah, exactly. 10 times 0.83. Yep. Yeah. No, find the Mach number using that 8.335. That's the PT9 over P9. Yep. It's the power. Yep. Exactly. 2.05. So M9 is going to be 2.05. Okay. Is there any questions? No. So part B is, let's go back to part B. Part B is actually, I'm going to give you this part as a bonus. And I want to calculate the nozzle area ratio for a perfectly expanded nozzle, right? And it's a convergent divergent nozzle. So the exit to the throat of the nozzle. What do we need to do? Of course, if you go back to the book, it, for whatever reason, it hasn't solved this part, but it has given you a clue. What do we need to do? Can we apply the conservation of mass? Yes, right. Conservation of mass essentially relates your pressures, right? Your m dots, right? And in your m dot, your velocities are included, the density is included. Using the ideal gas law, you can include the pressure and whatever. And we are all dealing with pressure ratios and the temperature and everything else here. So you should be able to start from the conservation of mass between the throat and the inlet, and also the throat and the outlet. And essentially find the properties of the throat, right? And also the throat. I mean, you want to find the ratio to make it simpler for yourself. You don't need to find the areas themselves. You just need to find the ratio, and we have the final ratio number to be 1.82, right? So if you do the calculations, and if you and you have to submit this bonus points by Monday. What day is Monday? October what? October 5th. Let's say October 5th. I will open a portal on. I will open on Blackboard so you guys can submit it. So we weren't able to cover what I wanted to cover, but we are essentially very close to the end. Yes, that's the idea. And the problems we solved. And your quiz is actually this time the quiz will be two problems, but two smaller problems, right? I assume you should be able to solve like two of these kind of examples in an hour, right? Because it's a very simple calculation. But 75, you had two huge questions on the first one, right? It's a little different. I mean, I can make it 75 minutes, but it's going to be a harder exam. Okay. Huh? Okay. No, so one of the questions, actually, I was thinking of one of the questions to be just an explanatory question. So you just explain a phenomenon, or you draw a like TS diagram or whatever, right? Something like that. And one of the questions will be a problem that you need to solve, like this one.
Have you uploaded the lecture files?
Not yet. No, I will upload them today because, yeah, no, I haven't. I used to upload them. I tried uploading them before the lectures, but then Tyler didn't print them out. So you do? You don't need to show you. No. Right? Okay. Please remind me then.
Can you make sure to do that? Because I'm sure there's a bunch of equations that I just didn't write down that might be useful.
Sure. I'll definitely do that as soon as possible. Okay, so that's gonna be it